Okay, hi everyone. I am Rahul Saladi, and I'm an assistant professor at the computer science department at IISc. So during the day, I do research and teaching on algorithms, and in the evening, I make sure I'm going to the ground and playing some sport. It could be these days mostly hockey, football, or frisbee. So this talk is something where I want to combine both. Right? Why should both be separate, right? So algorithmic sports, the idea is that I want to combine both algorithms and playing sports. Right? So what's the basic premise here for algorithmic sports? So I feel that for the next generation of high school kids, algorithms will be taught in high school itself. Just like that they are learning physics, chemistry, and math, I'm sure algorithms will also be taught to them in high school itself, right? And I feel it's our duty that we should make it as fun as possible for them. Right? When their first interaction with computer science should be as fun, not like the standard college style teaching. And then just the physical health of the kids, right? Right now, typically in many schools, if there's a clash between a PT class on the ground versus classroom teaching, it's always classroom teaching which is given preference, right? But why do we need that differentiation? Why can't we just combine both? Right? And in general, I mean, it's good to have a more active lifestyle, so I want to put the kids on the ground as much as possible. Right? So that's the premise for this algorithmic sports. So let me take a very concrete example here. Okay? So imagine I have 100 kids, 50 of them are from grade 10, and 50 of them are from grade 11. Right? So there will be some rivalry between them, right? Grade 10, grade 11. So what I'll do is, I'll take all of them onto the ground. So this is a ground which is colored green, not the IISc grounds right now, which are brownish. But right, what I'll do is, I'll ask the 10th graders, they are team A, right? They'll have to line up themselves like this, 1 meter apart, right? 50 of them are standing, right? Is that clear? Right. And then the 11th graders, again 50 of them, they'll all be standing like this, 1 meter apart again. Right? So that's step one. Right? So that's team A and that's team B, 50 on each side. Now step two is, just like have all of you gotten the numbers right now? Yes. So similarly, they'll also be given a bib which has a number on it. Right? Each one of them gets a different number. Right? So you see all the numbers there? So everyone has gotten a number. Right? So can you guess what the game now is? Any guesses? Sorting. Yeah, exactly. So that's the input. And now what we'll do is, I'll show you the output. So the game is, each team has to sort itself as quickly as possible. Right? So this will actually involve running around, coordinating, and making sure that you arrange yourself. You're not allowed to exchange your chits. Right? You just compare with each other, run around, coordinate. And now, as you can see, they are all standing now in increasing order. Right? Like team A, 147, 348, 462. That's the goal. Right? So that's the game. So now we have taken a problem from computer science and now we just converted that into sport. Right? Any questions at this point? The game is clear? Yeah, you can shout instructions, compare as quickly as you can. Yeah, you can do whatever. Yeah, so it will involve quite a bit of running around. Right? You can't push the other teams. That's why I've kept them quite far apart in this. Right? So you can't really, it's a non-contact sport. Okay, so what's the hope, right? So why are we doing this? The hope is that, the kids will really have the desire to win this sport, right? And once you have the desire to win, you'll naturally start thinking, right? How do I play this game well? Right? Once you want to win, how can I minimize the time to finish this game? Right? So naturally that desire will hopefully come into them, and then they'll start thinking on their own, or they'll at least be receptive to listen to what we want to teach after that. Right? So what would typically happen, right? Initially, if there are 50 players, the first time we ask them to play the game, I'm pretty sure it will be very chaotic. Even if I give them 10 minutes, I don't think they will be able to sort themselves in increasing order. It's not going to happen. Right? And then maybe we can give them a couple of more chances, and maybe some of them will start coordinating now. But if you want to really play this sport very well, you really need the coordination of all the players. And that's not going to happen right away. Right? So hopefully after playing this a couple of times, they'll be convinced, right, that, okay, this sport is challenging, and let me now systematically understand it, how to play this sport. Right? And hopefully once that desire comes, then they're ready to listen to whatever we want to teach. Right? So some interesting features of this particular sport is the following. Unlike the traditional algorithms, the sorting algorithms we teach in the class, they're all sequential algorithms. So how many of you have heard of this insertion sort, merge sort? Okay, almost all in here, right? So these are all sequential algorithms, right? But whereas on the ground, you can actually run parallel algorithms, right? People can actually swap parallelly, can do computation parallelly, right? So you can think of it as some distributed computing or parallel algorithm happening there. Right? The another interesting feature is, inside a RAM, right, when you ask that two elements have to be swapped, we assume that it can always be done in constant time, right? But that's not true on the ground. And if you look at those two orange guys there, they can swap themselves quite quickly. But then if two guys who are on black, right, if they have to swap, they're at the other ends of the ground. So their swapping would take more time. So technically, if you want to design an algorithm here, there are new challenges here. Because just minimizing the number of swaps won't be enough. Because the distance also matters, right? How far the elements or the players are. And then another interesting feature is data never gets tired, right? I mean, if you design an algorithm where you ask one data item to move around a lot, the data will never complain, right? But whereas a player has a limited stamina, right? So the player might get tired if you put too much work on a single player, right? If he has to run across the ground. So maybe so if you want to design an algorithm, a strategy here, maybe you might have to do some load balancing on individual players as well. Right? So those are some interesting features. And then, so one thing I noticed that in computer science, a lot of the action is missing out. Right? For example, aeronautical, right? They can show rockets are flying, helicopters, and very fancy stuff. But in our case, a lot of times I feel a lot of the nice action gets hidden. Because let's say we teach a sorting algorithm, right? So maybe you learn the sorting algorithm, you start programming it, right? You wrote the code, looked at the input, and what do you see, right? You write the input and then you just see the output. That's all, right? Whereas all the action, right, of all the swapping happening, all the moving around of the data is hidden inside the main memory. Right? None of them is actually showing up, right? But whereas if you actually convert that into a sport, and maybe if you have a drone shot, which is capturing all the activity happening, right, of the kids running around, it actually shows what is happening inside our mobile phones, right? All the computing that is happening. All of it can actually be shown to the whole world. Right? A lot of interesting stuff is happening inside. So all the action which is being missed can actually be unraveled now and shown to the wider audience. Right? So I feel there are some nice features here of playing these algorithmic sports. Okay, and once we have motivated students enough by playing these sports, the classroom teaching, again, we have just two models. One is a straightforward model where you can just go back to the classroom and the teacher can teach the standard sorting algorithms, right? And that's fine. And then the students will be sufficiently motivated now to learn them. Or the other model could be where you actually discuss this particular problem on how to do sorting better on the ground. Where, as I mentioned, there are new challenges, right? How do you overcome those challenges and design an algorithm? And even for young researchers, I feel this algorithmic sports or the sorting problem could be a nice playground for some fun research problems. Right? Because it's not at all obvious how to design a sorting algorithm for the setting I just described. Right? So I would like to hear inputs from you today and tomorrow, right, on what would be good strategies for that. So I think it's a fun way to get started into research as well. Okay. Okay, so now that I've discussed one problem, so let's spend a few minutes actually thinking about strategies on how this game can actually be played on a playground. So now let's look at a more simpler problem. So we'll not look at the sorting problem. We'll look at the problem of finding the max. Okay, max would be, okay, now let's imagine we have 256 players. Okay, there's a reason why I've chosen 256. It's a very friendly number. Right? So now imagine again we have a playground here, and now there are 256 players standing again. Think of them being 1 meter apart. Again, they have a number with them, a 3-digit number. And now the goal is to find the largest number. The problem is clear? right? Okay. I mean, this is easier to strategize, so that's why we are looking at this one. Okay. So let me discuss the first strategy, which is very simple. What would happen is, we'll just pick one representative. Right? Somebody will raise their hand saying that I'll be the representative. And then what will they do? Any inputs? Huh? Yeah. They just do a scan. They just run around the whole ground and then just do a scan or compare with everyone else, and they get the answer, right? So the number of comparisons that will happen will be 255, because you have to compare yourself with 255 other people and then find who has the maximum number, right? So in general, if there are n players, the number of comparisons that have to happen is n minus 1, and the distance that has to be covered might either be the length of the entire field or maybe twice of it. I mean, if you're in the middle, you might have to go till the end and again come back to the other end as well. Right? So it could be maybe twice the length of the entire field. Okay, so is this a good strategy? Nope. Okay, can someone explain how can we enhance this strategy, or what's wrong here? Yeah, please.
Tell two people, okay, to tell whoever is the maximum, come in the forward. Again,
okay, good. Yeah, you're on the right track. Yeah, that's a good, we'll come back to that, that's good. Any other strategies? Or what's wrong with the current strategy, or what's inefficient about the current strategy? Okay, yeah, it's linear. Yeah, what's the right word for it? It's too sequential. Right? Parallelism is not being used. Okay, so one strategy could be, let me slightly enhance this. Again, this 256 number has been carefully chosen. What will happen is, the first 16 people will group together, and they'll form one group. Okay? Like that, the next 16 people will come together and form another group. So like this, how many groups do we get? We get 16 groups, because 16 into 16 is 256. Right? And then the previous strategy that we applied, each group will apply within themselves. Right? Just the simple linear scan that we did, each group would do that within themselves. It's fine? So then everybody will find out who the max is from each group. Right? And then what do we do is, so how many representatives do we get now? 16, right? So one from each group. Right? And then what do we do? Yeah, so they come close together on the ground. And now it's just a game of 16 people playing this find max among themselves. Right? Okay, good. So the number of comparisons previously were 255. Now it dramatically, not dramatically, but at least significantly comes down, because when you were in the upper group, you had to do 15 comparisons. And now when you come down, you might have to do 15 more comparisons. So the number of comparisons have come down. Right? Okay, and then even the distance that has to be run by a player has also reduced now. Right? So it's only among 16 people you have to run 2 times maybe. Right? So even that's an important criteria, right? How much distance a player has to run. Okay, can we further enhance this? Okay, interesting. I've never thought about this shouting idea. Yeah, maybe that's possible, right? I didn't think about it. I was always thinking that they will actually visually look at each other and make a decision. Yeah, maybe that's also possible. So maybe that can be incorporated with somebody shouts, and then based on that you make a decision, you're saying. Use partition, okay. But for a moment, let's say we can't shout. I mean, can we enhance this strategy even further? Yeah. Okay. Okay, good. Yeah, so exactly. I think people are on the right track now. And I can't show it for 256 players, but let's say we have 8 players. And this is exactly what you guys are up to, right? So does this remind of something? This picture? So how many of you have seen a binary search tree? Okay, almost. All of you. Okay, good. So yeah, so exactly that's what you should do. What should happen is, think of these 8 players which are at the leaf nodes here. So every 2 of them just compare with each other, and whoever is the larger number, they will run slightly above in the field. So every 2 are doing that. Here 47 will go up. So that will be one round. Right? So the finding max on 8 players has been reduced to finding max among how many? 4. Good. And then you just, it's called recursion, where you just repeat this process now. Now this 47 and 85 will compare, and 85 will run to the top of the ground, slightly above. Right? So you just repeat this. Okay, good. So now just imagine this for 256 people. Right? So in general, if you have n players, and here n was 8, so the number of comparisons anyone has to make is at most 3 now. You can see that, right? That's just, if you look at 98, which was the max, it had to do one comparison here, second here, and third there. So no one has to do more than 3 comparisons. So we really made it parallel. We started with 255, then came down to 32. Now it's really come down to 3 now. Right? The number of comparisons anyone has to do. Right? And in general, if it's 256, oh yeah, it's 8 actually. Yeah. So now for 256, which was the original number we were looking at, the number of comparisons has come down to 8 now. Right? And in general, in terms of n, the number of comparisons someone has to do will be log n base 2. Right? And I think one can prove a lower bound, I feel, saying that some player has to perform at least log n comparisons. That cannot be avoided. I think that will be a good exercise for everyone to do. I think there will be at least one player who has to do at least log n base 2 comparisons. That's a nice exercise to do here. Okay, good. Right, yeah. So essentially, what's happening in each round is one comparison and run. Right? So we have divided into log n different rounds, and each round, all everyone has to do is just do one comparison and run a little bit to the center. Okay, good. Log n, okay. Okay. Yeah, yeah. Pretty sure this log n can't be avoided. I think. Yeah. Okay, good. So now I've mostly done. So why not just play a game now? Are you all ready to play a game now? Can I hear a yes? No. This is evening time, really time to play now, right? Yes?
Yes.
One final time. Are you ready? Yes. Okay, good. So I initially wrote max, but let's not do this. Let's do something more interesting. Shall we do sorting? Can we do sorting? Huh? Okay, so I mean, ideally I would have liked to take everyone to the ground and do it. Of course, we can't do it. So can we do it as a competition among rows? So every row has to sort itself as quickly as possible. Okay, let me make some rules clear. So the minimum person has to be on this side. You're not allowed to, okay, first of all, everyone has a chit? Everyone has a chit? Okay, good. And yeah, please make sure, hurry. Okay, the rules are the minimum has to be on the left and the maximum is on the right. Is that clear? Every row. The minimum has to be on the left of me, my left. And the max has to be on my right. And every row has to sort itself as quickly as possible. Video. So you're not allowed to swap your number. You have to retain your chit and play this game. You're not allowed to swap it with anyone. I need to see some urgency here. Some people don't seem to be that urgent here. No, the entire row. Just make sure the entire row is sorted. It's not just among 4 people you sort. Right? You really have to sort the entire row. Done? No, the entire second row. There are 4 people there. Oh, wow. Okay. The second row was the first to announce. And then the first row was the second. First row was the second to announce. Wow. Can you just verify? We need verification algorithm also here. It's from max to min. Harita, can you verify? Done? Wow. Okay. Manisha, can you check the last row? There are a lot of them and they said they're claiming they have. Can you verify, Manish?
Done.
You guys have sorted or not? You guys are so apart from with that row as well. The entire second. Okay, great. Done. Okay, looks. But the last row seems very impressive. It's a large collection of them, and okay, we have sent someone to volunteer to check if you have actually sorted yourself. Can you check from the right? Manisha is checking from the left. Sorry. Can I just have a quick check? No. 400, 485, 493, 501, 594, 640. Can I look at your numbers quickly? 6, 9, 9, 10. Wow. Okay, that was nice. And then can I have a check here? 9, 3, 947, 980, 98. Okay, there's a tie here. Interesting. Wow, that's nice. Wow. Okay. Can you just check for your neighboring rows as well? No, neighboring verification. Yeah. I can't. 9. Very technical noise. Stable sort. Okay. How do you break ties? 608, 689, 695. Okay. 77. Okay. Looks like, yeah, I didn't see any errors still. So how did the last row do? Manisha, they all done it. Wow. I think the last row was the largest. I think that's the most impressive I found. But the first one was the second row was that was easier, so I would know. And you have more space to run around as well. Like. Okay, thank you. Thanks a lot. Oh, okay. No. Okay, the talk is not yet over, but the game is over. Few more minutes. We are almost done. Yeah. Huh? Oh, okay. More hockey players are here. Very nice. Okay. What is the prize? Learning. Enthusiasm to learn sorting now. Like tomorrow's lunch. Okay. Yeah, so the numbers were slightly smaller in a row this day, but if you can really think about it, right, like there are 100 people, and you really have to sort yourself, and you want to do it very quick, right, really quick. You really need a very synchronized strategy, right? Airport boarding, airport boarding can easily choke the, okay. It really needs cooperation of everyone, right? Even few people not doing it right can, even in sorting, right? Even two people make a mistake and you're gone, right? So it really needs a synchronization among all the people, right? So that's the, grand vision I have is I want to make school education more fun. How can we just make it more fun? For example, we can have a simple website just based on this sorting sport where across schools, this game can be played and they can just share with us the timings, right? Maybe you can have some standardization and they can just share how well the kids are playing, right? So we could have a simple leaderboard like that. You can use any algorithm you want. You just have to finish sorting as quickly as possible, right? So it will really test the kids' algorithmic skills or the teacher's algorithmic skills, right? And the physical abilities of the kids and how well they're able to coordinate. It's a lot of skills are there to learn here. And they can share videos, right? Nice drone shots or regular videos of them playing this game. It just creates a nice ambience around learning algorithms, schooling, because we have all this technology these days, right? To share on Instagram and stuff, or just have a website, right? And just to, enhance learning, right? So hopefully students will be very receptive after playing a couple of times that whatever now the teacher teaches, they're ready to listen to them or critique it, think on their own, ready to program, and even do some mathematical analysis now. Usually a lot of times mathematical analysis needs more motivation, right? But hopefully this will inspire them, that will actually help them. It has a real consequence, right? They can play the game better and beat their seniors, right? So it can lead to more motivation. And finally, don't make fun of me, but why not have this sport at Olympics 2032? right? Because this is actually a sport. This is a very real sport. If you have 100 people who have to really play it as quickly as possible, it really requires a lot of skill. So there is some very serious sporting skill involved here. If you want to really play this game very fast, right? In terms of what strategy you want, it requires a lot of skill, a lot of strategy over strategy. You can get very refined, and athletic skills are also involved here. And the best part is, unlike some other sports like our hockey, which requires a lot of equipment, there's almost no equipment needed here in this sport. And in general, computer science has impacted the modern society so much that I can hope Olympics can give us one sport, right? One slot to play one sport of our own. Why not? That would be my dream. Okay, with that, I finished my last slide. So what I want is, if I can get some advice from all of you on what would be the right problem to choose, right? So that a small module can be built around it. So the requirements are, it should be a sport, not just a puzzle. It should actually be a sport where the kids can go on the ground, actually get tired, run around, play, right? And then to just make it complete, again, there should be some classroom learning as well. So I'm really looking forward for some advice from all of you on what would be the right problems to choose. For example, as a final slide, how many of you have heard about this traveling salesman problem? Right? So apart from sorting, even this can be a nice sport, right? Where you have 50 cones. Again, this is a brownish ground like the current IISc ground, right? Let's say we go on a ground and we have 50 cones, which are arbitrarily placed, right? And then the goal is somebody starts from there, and the goal is to touch and bring down all the cones as quickly as possible and come back. That's the traveling salesman problem. Now this is the sports version of it, right? So you have to touch all the cones and you have to return to the starting position as quickly as possible. So that's the sports version of it, algorithmic sport version of it. In fact, it can be made a multiplayer game where two players can coordinate together and play it, right? And typically, what happens is, it's okay if you have not heard about this term, but minimum spanning tree might be needed to efficiently compute a good tour. But clearly on a ground, after seeing 50 cones, nobody can compute a minimum spanning tree in their head. Right? So that strategy won't work. So what are the good strategies to come up with to play this sport so that you can come close to optimal tour here? Right? So maybe traveling salesman person is a good problem to convert into a sport. So like that, I'm looking for other ideas. Right? With that, I stop. Thank you. No, but the plan is there. Maybe this month or next month, I actually plan to go to a school, and I'm actually in touch. Yeah, this is my first time. Actually, I didn't tell you. This is the first time I have this idea from many years, but this is the first time I'm actually giving a formal talk on this. And yeah, most likely this or next month, I'll start reaching out to schools and. No, maybe after a couple of months, I'll keep you up. Yeah, I'll slowly start refining this. This is yes, Twitter. Yes, Ullas.
So, very interesting. I noticed one observation here that, you mentioned that the very first algorithm that we came up with was not really a good one because, one player just has to cover a lot of distance. But I'm just thinking in a school setting, maybe for the other kids, they might prefer that because they don't want to run around everywhere. They would like it if just one person does all the running around and the rest of them just sit back and relax.
Yeah, even I feel that. That's why I had 3 different strategies written down there. And I feel strategy 2 might be better, where you don't need all of them to be super active. Strategy 2 was where we had all these groups, right? So maybe that strategy might be more feasible in a setting. Yeah, this game actually requires everyone to be super active, right? So maybe if you want it at Olympics, maybe then we should have this strategy. But maybe at the school level, maybe even if you have a few active students, that should be enough, right? Yeah, again, maybe we can't. Optimal and yeah, that I agree. Yeah, but your point here is about willingness, right? It's not about athletic ability here. It's more about how many students are willing here. And Certainly. I mean, in the strategy 3, I'm assuming everyone is willing. But in strategy 2, I'm just assuming a square root of them are willing. Even that's good enough. Right? So I feel strategy 2 might be the sweet spot for school kids to start with.
At the start only you spoke about parallelism, but even the last algorithm which we discussed, it's not parallel, it's sequential. So what I know about parallelism is it's a single instruction and multiple data, or single instruction, multiple threads.
So, look,
Can we do it something like that?
No. Am I audible? Okay. But when I said one round, I meant all of them are comparing with their neighbor, right? So this is one comparison, this second comparison, third and fourth. So there are 4 comparisons happening in parallel. Right? So these guys will, at the same instant, these guys are comparing with each other, these guys are comparing with each other, and the next time instant, the winner is running here. So we are actually performing 4 instructions parallelly here, and then 2 instructions parallelly here. Right? So there is parallelism here. Right? So in that sense, yeah. So think of it as a one-time unit. People start here, in the second time unit they have reached here, in the third time unit they have reached there. So there's a lot of parallelism happening here. So is that clear? Yeah, okay.
Any more questions?
Okay, thank you. Thanks for playing the game. That was very nice. Yeah.
Let's thank Rahul for such a high-spirited session. Thank you.
Can I have one without the specs? Thank you. Thanks for introducing.
Yeah, just quick announcements for tomorrow. Please, repeating the fact that just hang on to your name card.